Hello everyone, welcome to the walkthrough of the Diffusion Models class Unit 1. This is the class that's offered by HuggingFace, and we're covering Unit 1 today. All the links will be in the description below. So in Unit 1, we're looking at the basics of how diffusion models work. There are some prerequisites for this though. They recommend that you do understand how PyTorch works, and how basic machine learning works as well. We're doing this walkthrough because even if you do know PyTorch, there are some things that you may not be aware of. So first, let's get started. What does a diffusion model do? In this diagram, it shows that when you have an input image here, you're going to add some noise to the input image. And noise basically just means some static here. Once you have noise to the image, that's going to be your input to the diffusion model. And then what the model will output is it predicts how much noise is in this input image. And we're going to compare it to the actual noise, comparing this predicted noise to the actual noise, and then update our model and keep going for the rest of the iterations. Now that's the basics of what a diffusion model does. Let's go over their Jupyter notebook here. So it tells you to install all these things. I've also noticed that you do need to install matplotlib and torch vision. So add these two lines here if it's not in your kernel. I'm using a Amazon SageMaker Studio Lab. They do recommend a few other things here. So you can use either Colab, Kaggle, Gradients, or the Studio Lab. It doesn't really matter which one you use. And then you have to go to HuggingFace to get their access token. All right, so then you can log in using the access token here. This function basically just lets you show images onto the Jupyter notebook into this sort of grid here. Now they're going to tell you a sneak peek of what will be coming later, which is Dream Booth. And Dream Booth basically it lets you fine tune the stable diffusion model for some custom images that you put in. For example, a lot of people are doing portraits, and you can train your own stable diffusion model on your own picture to get portraits in different settings. And then they're doing a example of Mr. Potato Head here. Now to explain that the minimal viable pipeline for the diffusers is split into three parts: pipelines, models, and schedulers. We're going to go into what these are very soon later on, and I'll do some explanation on my website as well. So this very first example, they're going to take this pipeline, and then they're going to get John Whittaker's already pre-trained DDPM model here and use that to create 8 images right here. So what is the difference between DDPM, this diffusion model, and stable diffusion? Well, first off, in this custom example, they're using much less data than stable diffusion. So of course the results are not that impressive, but this is just to show you how diffusion models work. And their training of diffusion model is exactly what we saw in this image here. So our next step, we're going to download a training set. And we're going to use this collection of 1000 butterfly pictures. So this line here is to load the dataset. Each image size we're going to be using 32. These are really small images, but we're doing this so that we can train fast and this is just for demonstration purposes. And the batch size is 64 as well. So we're going to do some data augmentations here. Um, so let's go over what these data augmentations are and what they're doing here. So you have to remember that what images really are. They're pixels with 8-bit integers, and they're between 0 and 255 for each of the RGB channels, right? That's how images are. But neural networks usually prefer floating point values in a much smaller range. So that's the reason why we need to convert and do some transformations here. So first one here, resize. It's pretty simple. We're just resizing this into a smaller image size so that we can train our neural net faster because there's small data to work with. And next, we're doing a random horizontal flip. So we randomly flip data so that we have more data to work with. To tensor. Also add a link here. What it does is convert our input image into this torch.float tensor, and you have this shape CHW in the scale. Why do we need to convert to tensor? So that it's in the data format PyTorch can use. C is channel, H is height, and W is width. So we have three. So C is channel, right? So we have three channels, one for each of RGB. The final step here, normalize. What does that do? Normalize here. It basically scales our tensor to a smaller range. And here we're doing this with a mean of 0.5 and a standard deviation of 0.5. And we have to do this because neural nets work better with a smaller range of floating point values. Now that's what's happening for the data augmentation. Yeah, this is all about transforming. And then we're actually going to use a data loader from Torch. What do data loaders do? Basically, it lets you serve up all your whole data set into batches. And our batch size for this example is going to be 64. And in this next cell here, they're basically showing you an example of what a small batch looks like for the data loader. And this is, we should probably take a look at here, the torch size. It's 4-dimensional here. So the first dimension means how many images we're showing here. The 3 means how many channels. And then this is just the height and the width, which corresponds to what we saw earlier in the transforms. Like I mentioned, we're sticking to a small data set of 32 pixel images just to keep the training times manageable. The next step is we're going to define a scheduler. So what is a scheduler? Well, basically, if we go back to here, our scheduler determines how much noise we're going to add to the input image each time. Now, they have this really fancy math equation here. It did take a bit of time to understand, so I want to go over that as well. So they have this equation right here. What does this equation mean? So remember that the input to our model is a noisy image. This equation basically tells you how much noise do you want to add to the input image each time step. Now the amount of noise you add is taken from this normal distribution. This is the mean and this is the variance. It still doesn't really tell you how much noise you're adding. So you use that reparameterization trick, and then you use this equation here. So 1 minus beta square root of that multiplied by x of t minus 1 plus square root of beta times the it's epsilon here. And then thanks to JM Tom Zach, this is what the code looks like for the forward pass here. So this is basically the reparameterization of the Gaussian diffusion. And basically, you have the torch at square root 1 minus self dot beta times x plus torch dot square root of beta times just a rand n like x here, which is basically the same as this here. So I found that it's a lot easier to understand what is in code compared to some of these math equations. Now that we understand what's happening here, they give you an example of what these look like. And next up, we're actually going to set a scheduler, a noise scheduler here. We're using a DDPM scheduler here with 1,000 training time steps. And we're using a predefined beta schedule. So remember, beta schedule is this here. We're just passing in a fixed value of what the beta is for this equation. Time steps, and then we're mimicking how much noise using this brand n like here. And this is an example of what that looks like. So at each time step, we're adding some noise. You can see, okay, this image has a bit more noise than this one. This image has more noise, and then you keep going until you basically can't even recognize it anymore, and it's quite noisy here. So now that we have this noise scheduler, we're going to define a model. And the model we're using is something called UNet. This image is a really good description of what UNet is. So this 128 by 128, it tells you the dimension of the input image. And at each step, you're downsampling. Downsampling basically means that you're decreasing the size of the image in half. Keep going until you reach this middle block. So in the middle block, our image is actually 4x4 from this 128 by 128. And then we have the next step where we're doing upsampling, and we're doubling the size of the image until we get back this 128 by 128. Now I want to go over this UNet model here. A UNet model is actually originally used for biomedical image segmentation. And it's basically a task where you try to identify each pixel of an image to a certain class. If you want to take a look at what the UNet model looks like, I found that this is actually a pretty good example. So let's take a look at the forward pass here. So we start off with 512 by 512. This is just an example. And then each time there's really two steps. We create a convolution here. And then after max pool decreases the image size in half. And you can see the same pattern happening. You create convolution, then you do a max pool until you get down to the image size that you need for the middle block. And then we call this the center block here. And then you do upsampling. Upsampling basically, so up underscore concat, what is that? Underscore concat, you do a UNet up. And that doubles your image size each time until you get to the final output. And the final output is where you have the same image size as the original. So Diffusion provides us with a really handy UNet 2D model, which helps you create that architecture. And it actually looks pretty similar to the code, but a bit more abstracted out. You have down block types, so you have 4 blocks here. And then you have up block types where you define the 4 blocks, which is basically here. Each block is this. How many channels? We have 3 channels because we have 1 channel for each of the RGB channels, and our number of output channels is the same since we want that to match. So we have that model here, and then here we're looking at, just to make sure that we have the shape of the model that we want here. 8 by 3 by 32 by 32. Next up, we want to create a training loop. So each batch of the data, we're going to just sample some random time steps, add noise to the data, feed that noisy data through the model. We're going to compare the model predictions with the target, And we're using mean squared error as our loss function. And then update the model parameters using loss.backward and optimizer.step. So because this code takes about 10 minutes to run, I ran it ahead of time. Now let's take a look at how the training loop works. First, we're going to set up the noise scheduler, and it'll have 1,000 training time steps. Here's the optimizer. We're using Atom W. We're going to keep the losses here, and we've initialized that we're going to do this loop for 30 times. And then we're going to iterate over the data loader here, grab our images, we add sample noise to the images here, and then we're going to sample a random time step for each image. Once we have to, and then add a noise to those clean images at each time step. We get that model prediction, we calculate the loss using a mean square error between the noise prediction and then the actual noise here. And then update our model using a backward and add the losses here. Update the model parameters using the optimizer and then zero out gradients. So I ran this ahead of time, and here is what it looks like. See the losses decreasing for each epoch. And we can also plot out the losses here. And you can see that we're continuing to get better, but at a slower rate. Now, after we have that model, we can actually generate images. There's two options here. The simplest, this is the easiest option. We're going to use the DDPM pipeline from the Diffusion library. So you basically just plop in the model here and the scheduler, and it outputs the butterfly automatically here. You can save it there as well. I won't go over that. The second option, this is a bit more involved. We're going to be writing a sampling loop. So you can actually see what happens in the forward method of that pipeline here. So we're going to get a random starting point. What does this mean? Remember, this model requires you to pass in a noisy image. So it doesn't really matter what sort of image you pass in. That's why we're using a random starting point of 8 random images. So 8 images here, 3 channels, and each one is a 32 height, 32 width. And we're going to randomize that, and that's going to be our sample. And we're going to enumerate over the noise scheduler for 1,000 time steps. Get the model prediction, and then update the sample with that step here, the noise scheduler step, using the previous sample. And then we'll see that the images will turn out from random noise all the way to butterflies here. So what's the noise scheduler step? It does that math that you need to do to update the sample. So it's updating the sample in place appropriately. And they mentioned that in the next unit, we're going to see how we can swap in a different sampler to speed up image generation and the theory behind sampling from diffusion models. And that's it. They do cover some other stuff, but those are more optional. What we covered here is the gist of it. So if you do like this, please like and subscribe, and all the links that are shown here will be in the description below. Thanks.